Ladies and gentlemen, good morning. So I would like to welcome everybody here for today's defense of PhD of Moritz Krüger. My name is Tomasz Chrzanowski, and it's really my great honor to be here and to be a chair of that defense, which title is Complex Optical Networks Based on Vertical Cavity Surface-Emitting Lasers. And of course, I would like to welcome three other persons which contributed to that thesis. First is Professor Dr. Ingo Fischer, who is a thesis supervisor. Dr. Daniel Brunner from Institut Femto ST Université de French Comtesse UNRS Besançon, who is a second thesis supervisor. Professor Dr. Pere Colette Refecas, who has been a thesis tutor. And I would like also to welcome thesis reviewers, Professor Barbara Piętka from University of Warsaw. Her scientific expertise lays mostly in the exciton-polariton condensates, liquid crystal optical cavities, and neuromorphic computing in a regime of strong and weak light matter coupling. Professor Antonio Hurtado from Institute of Photonics, University of Strathclyde, Glasgow, United Kingdom. Professor Hurtado's main areas of research interest are neuromorphic computing and artificial intelligence, with a special emphasis on ultra-fast artificial photonic spiking neurons and their networks, as well as optical spike-based processing platforms. As for myself, I'm from Institute of Physics from Technical University of Łódź, and my main expertise lay in the development of numerical methods for optical modeling of VCSELs, designing of VCSELs, and also numerical simulation of photonic structures. And here I would like to mention another person without whom we would not meet here today. I mean, Professor Stefan Reisenstein, with whom Moritz was collaborating some time ago. And Professor Reisenstein came here like in 2014 and met Ingo. And he, for the first time, mentioned a very talented young man who today is giving his PhD defense.
That's actually not accurate. Like in 2014, we didn't know each other. but like it might be accurate that I'm here due to them meeting, but not.
However, Stefan asked me to send you his. Glück for today. So,
thank you very much, Tommy.
And I have also information to all of us that there is a kindly remind that everyone not applaud after the candidate's presentation. Okay. And so you're familiar with it. And before questions of the committee, there is a chance to leave the room if you would not like to participate in the second part of the thesis defense. So Moritz, this is the time for your presentation. You have 1 hour, and please show us the most important results of the PhD defense.
Thank you very much for the introduction, Tommy. So, as mentioned, the title of my PhD thesis is Complex Optical Networks Based on Vertical Cavity Surface-Emitting Lasers. The short form for this bulky word is VCSELs. So as usual for PhD defenses, this is quite a bulky title. However, if you asked anyone in this room what my PhD is about, they probably would have known that it is about lasers, about something with lasers. So let me start by explaining to you what's the difference between a laser and this object. Well, this object is designed for a very specific purpose, to solve a very specific problem, which I think all of you can imagine which it is. The laser was not developed for one specific application. Actually, after the first demonstration of the laser, researchers referred to it as a solution looking for a problem, because they were expecting it to find applications in many areas, but they didn't know which applications yet. Still, they were proven more than right. The laser today is used in a huge variety of fields. It's used for printing, in medical applications like refractive eye surgery or tattoo removal, in laser cutting, in optical tweezers, in optical fiber communications, for reading optical disks, and in this little device that due to which I'm able to point on this slide. So the main properties of lasers that are exploited for these applications are the high coherence of the laser light, the high beam directionality, and the high output powers of lasers. However, especially for semiconductor lasers, there are other properties that you can exploit or investigate, which are their extreme sensitivity to feedback and coupling. And due to this, there has been a lot of investigation into coupling semiconductor lasers. So here I'm showing you a few different approaches that have been taken. So for example, semiconductor lasers have been coupled in fiber networks, in free space setups, or they have directly been built in a way that would favor coupling. For example, here where they couple evanescently, or in a newer approach, there are topological insulator lasers which couple on the surface of the topological insulator surface. So as I said, coupled lasers and lasers with feedback allow studying many interesting phenomena, and with this you can get very creative for different applications, of which I'm going to show you a few now. For example, you can use lasers that are chaotic due to feedback for random bit generation. In another application, a secure key exchange protocol has been established thanks to chaos synchronization between semiconductor lasers. And another thing you can use lasers for is information processing. This is a setup where they implemented a deep neural network with VCSEL arrays. So why would you do that? Why would you use lasers or optics or photonics in general for information processing? First, let me tell you that optical computing is not a new idea. I was very impressed to learn that already in the early 1990s, the group of Demetri Psaltis achieved this impressive feat of all optical face recognition. So the all optical network learned or was trained to recognize a face, and then that a light emitting diode would light up when it recognized the face. It's not working perfectly, but it's absolutely impressive that they could do this in the 90s. So this has been researched in the 90s, but it has regained attention lately due to the following reasons, which is that now, since the early 2010s, there has been a new advent of artificial intelligence applications. And as you see here, the operations needed to train artificial intelligence models have been increasing for a long time, but since the early 2010s have been increasing ever more steeply. So why is this a problem? Well, because this uses a lot of energy. The current energy use of ChatGPT is estimated to be equivalent to the consumption of gas and electricity of 80,000 average Spaniards. Data centers and data transmission already are responsible for about 1% of the global greenhouse gas emissions, according to the International Energy Agency. And according to another estimate, a comment published in Joule, by 2027, AI servers could use as much electricity as the whole of the Philippines, a country home to more than 110 million people. And the problem is that when you increase the performance, when you increase the operations, you will also increase the power you need with the current hardware. I mean, you see some outliers here. You can optimize this, but only up to a certain point. The hope lies in using different hardware, because we all know we have different hardware in our head that does similar tasks very efficiently. But you could also use different hardware like optics and photonics. Optics and photonics offers a lot of possibilities for computing, for analog computing. It can be very energy efficient due to energy efficient or even passive components. It can reach high bandwidths, which can allow for fast processing of the data, for high data rates. And it's a mature technology, which means that many of these components are commercially available. That's why there has been a lot of research into this. Here I'm going to show you a few examples. For example, this publication where they build a diffractive deep neural network. So the layers of this network are diffractive layers, which means that once this is trained, the inferences are completely passive, so don't consume any energy. Then in this example, Antonio's group imitated the dynamics of, or the behavior of neurons in the brain using a vertical cavity surface emitting laser. And here, this is a reservoir computing approach where they established the neural network, or the central network, the reservoir, using a scattering medium, which is also completely passive. So in all this, what is our approach? What is our contribution to the field? What am I going to present today? We will use several lasers, VCSELs to be precise, that are coupled optically, diffractively in an external cavity. With this, we will establish a network, which could also be a reservoir. I'm going to get to this in a minute. We have the possibility to input information into this network using an injection laser and modulating it. And we can get output. We can output this information in this layer. So what is this reservoir computing I've been talking about? At the heart of a reservoir computer lies the so-called reservoir, which has fixed and recurrent connections. This is why this is a hardware-friendly approach, because you don't have to train these connections. You can use a system that is connected and don't worry about the internal connections. Then usually the input weights for inputting information are fixed. In newer approaches, they can also be trained, but they don't need to be. And now the reservoir nonlinear transforms the input into a reservoir state Q, which contains the state of all the nodes at all the times, or in other words, the response of the reservoir to every input. The output is obtained as the product of the reservoir state with the output weight vector. And this output weight vector is determined in a process called training, which in reservoir computing consists of mainly a linear regression. So here you just minimize the distance between the target and your output, and then you have a scalar here to avoid overfitting and ill-conditioned matrices. So let's wrap up the motivation for our research. There's a fundamental interest into coupled lasers as complex network test beds. In our case, the complex refers more to the interaction than to the network topology. This is, among other reasons, because there are similarities between optics and other real-world systems. For example, due to their similar mathematical description, rogue waves in oceans can be studied by investigating light fields in optical fibers. And zero-lag synchronization can be found in brains and between lasers, to give two examples. And last but not least, we want to implement a reservoir computer to process information. And in our reservoir computer, then all the nodes will be physical. What is the hardware we use for this? As in the title of my thesis, those are vertical cavity surface emitting lasers, to which during the rest of this presentation I will refer to as VCSELs. VCSELs are a type of vertically emitting semiconductor lasers. As usual for semiconductor lasers, you achieve a polarization, a population inversion via electrical pumping. VCSELs have distributed Bragg reflector mirrors that are defined in epitaxial growth via epitaxial layers with high refractive index contrast. The active region, in many cases, and in our case, consists of several layers of quantum wells. And in our case, the aperture is defined by oxidation into predefined layers. VCSELs have various advantages compared to edge emitters, which are, one big advantage is that you can test them on chip. Another is that they have a circular beam profile, which facilitates coupling into fibers. They have a low beam divergence, and one advantage of which we will take advantage is that they are arrangeable in 2D arrays. And these are our arrays. These are the arrays we're using. So our arrays consist of 25 VCSELs arranged in a 5x5 square lattice. So every single dot of these is one laser, basically. They were custom manufactured at Stefan Reitzenstein's group by Tobias Häuser, as Dominik mentioned. And so the pitch between the VCSELs, we could define the pitch between VCSELs, which is about 80 micrometers in our case. This is important for our coupling scheme. The aperture of the VCSELs is about 5 micrometers to aim for single mode emission at low pump currents. Importantly, our VCSELs are individually addressable because they are individually electrically contacted. In our case, 22 of 25 are independently tunable because we have 3 short circuits between pairs of VCSELs. And here you see how they are individually contacted. So you have these contacts that contact to the bonding pads. Then the sample is placed on a submount. This is wire bonded to the submount. The submount is placed in a VCSEL mount and finally connected to a printed circuit board, which was also custom designed for these experiments. And well, I'm not taking credit for this. This was work done in Brunner. They are homogeneous regarding threshold currents and slope efficiencies, as you see in these Li curves. As I said, we aimed for single mode emission, and in our VCSELs, they emitted single mode close to threshold. The ground mode is a single lobed circularly symmetric LP01 mode. In our case, there was a side mode suppression of at least 15 dBs for pump currents below twice the threshold current for all the VCSELs in our array. So to show you that the VCSELs are spectrally homogeneous, let's first have a look at a spectrum at high pump currents. Here you see the ground mode, the first order mode, and the second order mode. And what we did in these plots was that we stacked these spectra. So we color-coded the spectra and recorded one for every pump current, and then or for many pump currents, and then stacked them. From here, we extracted the peak of the emission wavelengths of all the VCSELs. And this is what you see plotted here. So this shows that the VCSELs are spectrally quite homogeneous. They, at similar pump currents, they emit at nearly the same wavelength. And the outlier here is actually the central VCSEL, which was actually lucky for us. I'll get to that later. All of our VCSELs, or nearly all of our VCSELs, are linearly polarized and homogeneous regarding their main polarization direction, as visualized in this plot, where we varied the polarizer angle and measured the optical power throughput. And just to give you an idea of what the mode profile looks like, here you have the ground mode, and then when you increase the pump current, you see different modes appearing. All these beam profiles are separated by polarization using a beam displacement prism and by wavelength using a grating. So up to now, we have only talked about the single VCSELs, but the aim was, or the goal we had was to couple them. So how did we do that? We established coupling between nearest and second nearest neighboring VCSELs with a diffractive optical element in an external cavity. And the condition for coupling is given by this expression. I'll derive this expression in a minute, but for the moment, notice that the variables that enter are the pitch of the VCSELs, the focal length of the microscope objective, the wavelength of the VCSELs, the emission wavelength, and a grating, the DOE constant, which is similar to the constant of a diffraction grating. So let me explain to you in a 2D ray optics argument how we derive this equation. Here we have the VCSEL array. We collimate the emission, which means placing a microscope objective one focal length away from this array. Then it passes the diffractive optical element where beam copies are created. A lens focuses the emission on a mirror and it's reflected back to the array finally. So now the difference between the angle at which the emission of different VCSELs passes the microscope objective is given by P divided by FMO in the paraxial beam approximation. The difference between the angles of different beam copies after the DOE is given by this expression, which is similar to what you obtain for a diffraction grating. Now, for the emission of different VCSELs to overlap at the mirror, these angles have to be of the same magnitude. And when their emission overlaps at the mirror, finally, it will also overlap at the array, because on the way back through the cavity, like here we have unfolded the cavity, on the way back through the cavity, we basically have the same condition for coupling. So here I plotted I sketched the emission of different VCSELs in different colors and the different beam copies or diffractive orders at the diffractive optical element with different line styles. Only for the red dashed line, I also sketched the splitting at this second pass of the diffractive optical element. And this shows that here the emission of the central VCSEL is coupled into a nearest and a second nearest neighbor. This is in 2D, but it also works for 3D. So it also works for the coupling of the light of the central VCSEL into the corner VCSELs. This coupling concept is scalable up to some point and up to a certain point also reconfigurable. And it allows for simultaneous optical injection into all the VCSELs when you do the following. When you place you can use a beam splitter to couple the emission of an injection laser into the external cavity. And when you align this with the emission of the central VCSEL, then you will also couple into all the VCSELs of the array, as shown before. So I just explained you the heart of our experimental setup, which are the VCSELs and the external cavity. Then our setup also contains a part for injection, as I said, an injection laser, and the possibility to modulate its intensity using a Mach-10er modulator, which is connected to an arbitrary waveform generator to control this. This is all done in fiber. Then this beam is coupled out of the fiber and collimated using a lens, and finally aligned in polarization to the polarization of the VCSELs. The purpose of this beam splitter is twofold. As I just said, it serves for coupling the light of the injection laser into the external cavity, but also for coupling the light of the VCSELs out of the external cavity for measurement and alignment. Here we have a single mode fiber as an alignment reference, and here we can use the light of the VCSEL, couple it into fibers and measure it using all of optical spectrum analyzers, electrical spectrum analyzers, or oscilloscopes. Before getting to the results for coupled VCSELs, one result for solitary VCSELs, but with feedback. We want to be sure to not confuse the effects of feedback with the effects of coupling. So for the central VCSEL with self-feedback, we observed a threshold reduction of 3.5%. That's without the DOE placed in the external cavity. And we observe external cavity modes in the radio frequency spectra. Those are peaks at the inverse of at multiples of the inverse of the external cavity round trip. And here you see a difference between the measurements with diffractive optical element and without, which is that the optical cavity becomes optically longer with the DOE placed in it. So now let's get to the actual results of the thesis. First, what we did was that we investigated pairwise coupling. And you could now just brute force investigate the pairwise coupling between all possible VCSEL pairs, but that would take ages, I suppose. So what we did was we just set the pump current of the central VCSEL to 1.3 times the threshold current and varied the pump current of one additional VCSEL and switched off the other VCSEL. So what we investigated basically was the coupling between the central VCSEL and one additional non-central VCSEL. And then we recorded optical spectra and radio frequency spectra for different detunings between these two VCSELs. And what do you see here? So here first you see this vertical trace. This vertical trace is the emission of the central VCSEL. Then you see these diagonal traces, which show the emission of the additional VCSEL that is reflected at the top facet of the central VCSEL. And what we observe here clearly is a shift at one point of the emission frequency of the central VCSEL to the emission frequency of the additional VCSEL. This is a clear signature for optical injection locking. Parallelly, in the radio frequency spectrum, we observe a suppression of autonomous dynamics. And now we did this for this additional VCSEL, but we did this, of course, for all the additional VCSELs. Here you see an example for another VCSEL. And in the optical spectra, we observed locking in 14 of 21 cases. That we didn't observe it in all of the cases might be due to the limited resolution of our optical spectrum analyzer, because we observed signatures in the radio frequency spectra in all these cases. Now we wanted to quantify the coupling. How did we do that? Well, we extracted the peak positions of the emission of the optical spectra in these scatter plots. So here they are given for these two cases. And then we compensated for the heating of the central VCSEL by the pumping of the additional VCSEL. So when you pump another VCSEL on the array heats up, and the emission of the central VCSEL is also redshifted due to that. So to compensate for that, we have these linear plots, and we determine the upper locking boundary as the difference between the scatter plot and this line plot. And then we can use this proportionality to calculate the coupling constant. For this proportionality, we have to estimate this ratio between the optical power of the additional VCSEL and the optical power of the central VCSEL at the top facet of the central VCSEL. We estimated this and calculated an average coupling constant for pairwise coupling between 13 per nanosecond and 29 per nanosecond. This will be compared to later values because as such, the value is a bit floating in the air. So the next kind of coupling that we investigated was entire array coupling. Now all the VCSELs of the array were switched on. As in the case of pairwise VCSELs, we constantly pumped the central VCSEL at 1.3 times its threshold current. And then we set the wavelength of all the other VCSELs to a common wavelength. So we tuned all the other VCSELs as far as we could in resonance and tuned this common wavelength via the pump current of these additional VCSELs. And then again, we recorded an optical spectrum and then a radio frequency spectrum at every step. So what do we see here? Of course, here again, what overlaps is the emission of the central VCSEL and the reflection of the emission of all the other VCSELs at the top facet of the central VCSEL. But we also have two lines here. This green line is again the wavelength, the peak emission wavelength of the central VCSEL that we expect just due to heating of the array. Like this is not constant, this is not a vertical line, because when you increase the pump current of the additional VCSELs, the array heats up. And then the red line is the peak of the VCSELs of the ensemble without the central VCSEL. So for recording this, for determining this experimentally, we switched off all the other VCSELs and just recorded the reflection. And what we observe here now is that, especially here you see it clearly, that the emission of the central VCSEL is shifted towards the emission peak of the ensemble VCSELs. But this peak of the central VCSEL reappears at higher detunings. Simultaneously to this transition in the optical spectra, we have a transition in the radio frequency spectra, where we see that dynamics below 3 gigahertz appear. And why does this happen? Well, actually, due to the bitwise nature of our pump current control, we cannot tune the VCSELs completely into resonance. There are residual inhomogeneities of up to 10 picometers, which corresponds to 3 gigahertz. So this is what we see here. We see these residual inhomogeneities of up to 3 gigahertz between the different VCSELs, because here the VCSEL unlocked. So we conclude that below this, the entire array was locked. To corroborate our claim, we calculated the coupling constant, which is comparable to the coupling constant for pairwise coupling. Since the proportionality from which we calculate the coupling constant assumes a single monochromatic source and not several VCSELs with uncorrelated phases, we conclude that we succeeded in locking the entire array here. So how does that help us, locking these VCSELs? The thing is that by proving that we have locking between the entire array or pairs of VCSELs, we actually prove that we have established a network of diffractively coupled VCSELs. These findings have been published in Optics Express as well. Good, so let's get to the next part. Up to now, we have only used the VCSELs and the external cavity and the measurement arm. Now we will also use the injection part of our setup. Still without modulations, so just with an optical isolator, but of course with the injection laser. What we did now is that we set all the VCSELs to a common wavelength, and we tuned the injection laser wavelength. And here you have 4 examples of what we observe. Actually, we observe optical injection locking to the external drive laser for all the VCSELs. How can we be so sure that we observe this? For nearly all the VCSELs, we observe a side mode suppression, the upper boundary for which is given by this vertical green line. And for all the VCSELs, we observe a shift of the emission peak. These peaks are given by these scatter plots here, and we can use both methods to determine the upper locking boundary, and both methods yield pretty much the same result. With this, we can again calculate the coupling constant from the proportionality given before, and again we obtain a coupling constant of the same magnitude in the same range. Now, when we plot all these scatter plots here into one scatter plot, we notice that for certain injection laser wavelengths, all these inhomogeneities disappear and collapse into not 1 point, but nearly 1 point. So to see how many VCSELs we can lock at once was that we slightly modified the VCSEL pump currents, but then set them to a constant value, did not touch them anymore. Same for the injection laser wavelength. And then we isolated the effects of feedback and injection, and we found that actually for all 22 individually tunable VCSELs, we can lock them simultaneously to the external drive laser. This helps us since with this, the external drive laser, with this we can use the external drive laser to input information into the system. And this has been published together with the results on locking in Optics Express as well. So up to now, we have just injected a constant injection laser intensity into the VCSELs. What we do now is that we will use a Mach-Zehnder modulator in combination with an arbitrary waveform generator to modulate this intensity. We will modulate this intensity at about 450 megahertz, which is equal to the external cavity frequency. And we will inject a series of random numbers. Then, using an oscilloscope, we measured 3 different time series. One is directly the intensity modulated emission of the injection laser, he plotted in blue. One is the reflection of that signal at the top facet of a switched off VCSEL, which is this curve in red here. And then we switch on that VCSEL, and that's the response of the VCSELs to the intensity modulated injection. What we observe is that the reflections at the VCSEL surfaces reproduce the modulation close to linearly. As you see, these 2 lines are different in magnitude, but they lie pretty much one on top of each other. We also observed that the VCSELs can implement a nonlinear transformation of the input signal. To visualize this, we have these plots on the top right. From these oscilloscope time traces, we extracted average of subsequent points, discarding points for transition. By this, we obtain the green dots. The green dots are the response, or we define the green dots as the response of the VCSEL to the injected random number. And then we plot these responses against the injected random numbers. And as you can see, for these 2 VCSELs up here, these are 2 examples of where the input is nonlinearly transformed. In some cases, the input is just linearly, like the transformation is only linear. And in some point, for some VCSELs, we have a problem with the signal to noise ratio. For about 5 VCSELs, we could mainly just measure noise. However, this nonlinear transformation made us optimistic to try to implement reservoir computing with our system. So how do we do that? I've already shown this sketch. Now I will go into more detail. Our VCSEL reservoir computer consists of a reservoir, of course, which is represented by the coupled VCSELs. The connections between the nodes of the network are implemented diffractively. We have a linear reservoir for comparison, which are the reflection at the VCSEL surfaces. The input is the intensity modulated injection laser. And in our reservoir computing experiments, we usually injected 1,000 values, series of 1,000 random bits or random numbers. The output, well, the reservoir state is given by the VCSEL responses. And for the output, the training is carried out offline on a conventional computer, since we needed to record the VCSEL responses one by one. Of these 1,000 samples, 800 were used for training and 200 for testing. And we used 5-fold cross-validation, which means that we used each sample once for testing and 4 times for training. Finally, we tested the system on 4 basic benchmark tasks. And these tasks were, number 1, a memory task. Here, the input consists of random numbers. And this task actually consists of several subtasks for different natural numbers k. So the target output is the input from k steps ago for a certain subtask. So when k equals 0, the target is just to reproduce the current input. When k equals 1, the target is to reproduce the input from 1 step ago, and so on. From this, we can calculate the memory correlation, which is the squared Pearson correlation between the target output and the actual output of the system. And then you can calculate the memory capacity of the sum over the memory correlations. In theory, this sum goes up to infinity. In practice, you stop at some point because the contributions become principally negligible. We summed up to k equal 10. And now we tested this, varying 2 parameters. One is the average injection ratio, which is the average ratio of the power of the injection laser and the VCSEL at the top facet of the VCSEL, and the other one is the average detuning between injection laser and VCSELs. And here on the left you see this for different average injection ratios. Here on the right you see this for different detunings. And what we observe is that we have the best performances for higher injection ratios. So here for 0.2 and for 0.13. We obtain a maximum memory capacity of about 3.6. And we also observe that the linear reservoir has a high memory correlation for k equals 1, but then this memory breaks down. This can have two reasons. Either that we injected the data at the external cavity frequency, so the information injected one step ago just got back to the array at that time, at one step later, or this could also be due to correlations between subsequent points, subsequent samples of the arbitrary waveform generator. The next task that we tried was digital to analog conversion. Here, the input consisted of random bits, and the target for m-bit digital to analog conversion is to map the last m bits to a value between 0 and 1. So for the case of 2 bits, we map 0, 0 to 0. We map the 2 bits 1, 1 to 1. We map 0, 1 to 1/3 and 1, 0 to 2/3. Please notice two things here. So one is that we only used the reservoir state that corresponded to the input of the last bit for this task. And the other one is that the last bit is actually the least significant bit. This way, we make sure that the task increases in complexity when increasing the number of bits. And what you see here, where you have the reservoir output plotted against the target outputs, is that for 2 bits, this works quite well, while for 3 bits, even in the best case, this kind of breaks down. Our measure for this is the root mean square error. And here we have plotted the root mean square error against the number of bits for different average injection ratios. And we also have the trivial guess of always just guessing 0.5. And as you see, for higher numbers of bits, this breaks down, but for 1 or 2 bits, we have good performance, at least for high injection ratios. The next task we tried was the exclusive OR task, which is important because it's a nonlinear task. Here the input is again a random bit sequence, and the target for m-bit XOR is the sum of the last m bits modulo 2. In the case of 2 bits, this just means a 0 when they are equal and a 1 when they are not. Here we thresholded the output because only binary outputs make sense. And we measured the performance via the bit error rate, which just means the percentage of times this predicted the wrong outcome. And as you see, for 2 bits and high average injection ratios, we obtain low errors, but this error increases a lot when moving to 3 bits. But you have to say here that 3-bit XOR is already a quite complex task. And again, here we obtain the best performance for high average injection ratios. The last task we tried was header recognition. In our case, the header recognition task consisted of several subtasks. So the target for the subtask correspond to the different m-bit headers. So for example, you pick one header, here 0, 1, 1 is a 3-bit header. And then the target output is 1 when the last 3 bits correspond to this header, and 0 if not. Now you do this for all the possible headers, and then you average the result. Here the output again is thresholded because only binary outputs make sense. And again, the measure for the error is the bit error rate. And as you see here, for a high injection ratio, we managed to perform this error-free. And then this increased quite a lot again for higher numbers of bits. As you see, the trivial guess gets better and better because trivially guessing 0 is better and better because the percentage of headers where you want to have a 1 decreases with longer sequences. For all these reservoir computing results, a publication is in preparation. Okay, so let me wrap up what we did. We investigated diffractive coupling and injection locking for VCSELs in an array. We found evidence both for pairwise and for entire array locking. This is evidence that we established a network of diffractively coupled VCSELs. We managed to simultaneously injection lock 22 of 25 VCSELs to an external drive laser, which means that it's possible to input information into the system. We found that the VCSELs respond nonlinearly to injection, which means they implement the nonlinear transformation needed for reservoir computing. And finally, we carried out reservoir computing with our diffractively coupled VCSEL network. A short outlook on that. First, a setup specific one. In our setup might benefit from a stronger injection laser, since we obtained the best results for high average injection ratios. We could use a spatial light modulator, both for implementing an optical output layer or to replace the cavity mirror. There we would get gain reconfigurability. The advantage of an optical output layer is that we could read out the response of all the VCSELs at once and would not have to do all that offline. We could combine this concept with delay reservoir computing to increase the number of nodes, which usually also improves the performance. Or we could create larger networks using quantum dot micropillar lasers. In a more general frame, I think VCSEL arrays used as deep neural networks are a very promising approach, but even so, there's definitely more research needed into non-conventional computing to face the possible energy problems that we have. Thank you very much for your attention. I'm looking forward to your questions.
Thank you very much. So this is a very tricky moment that we should not applaud after the presentation. And if you have other things to do right now, this is the moment when people who are